here. So you'd say, oh, okay, well, what f squared is just this, right? But remember, you've got to be careful about that new summation index. You don't want to get it mixed up with the other one. So we know what that is it would just be the sum of these things. Like this, right? Now the thing is, you know what the average of that is. We just showed it. We just showed that that thing is 0 if I doesn't equal j. And it's non-zero if I equals j. So what's happening is all the cross terms are vanishing on averaging. It's only, what's all that's happening is you're getting the diagonal term. The A1, B1, the A2, B2, 1. So if we averaged, what would happen? We would just have the sum of what? Fi squared. And so this is f squared. This is the magnitude if we were to just average. So then someone could say, well, how big is a force do we get? Well, you could try to estimate just by taking the square root of this thing. So what is that the same thing as doing? It's like the standard deviation. You want to figure out how big the errors are around 0, or what about the average. You look at the differences from the average, you square it, add them all up, average them, take the square root after. And so that's basically all that there is on this. I mean, basically that's, you just square root each side, and then you get this last line right here. And so that would tell you basically how big that force has got to be. Right? So you have to find out what's the magnitude of all the mistakes, right? And you can, well, there's a way of getting that. It's like the next part, we mentioned it. Add them all up for each one, and then take the square root, right? So that's how big we would expect the force to be, right? So if we were to look at that, the value, like that when you drew your little diagram or you did your algebraic way of adding them, what we would expect is that the net force, we would expect to be what? It should go like this sum of all of these guys. Look at the sum of those errors like that. So that's, we call that, I call it delta F in here. So magnitude, right? So we call this delta F in the lab. It's the magnitude of that net force. So all we got to do is we just got to figure out how big each one of those is. And that's the next two questions. So it's pretty much just like we showed you. Again, in the lab, this is just putting mathematical kind of meat on that, those sort of, not to be too metaphorical here, on those pictorial bones that I showed you last week, right? We're putting just mathematical kind of consistency to it now. So here's your F, and here was your delta F, right? So we made some mistake that looked like this. So then we said, okay, look, this guy actually had two pieces. It had a piece like this, we call that delta F parallel, and we said it also had a piece like this, right? Yeah? Mm-hmm. There were two parts to it. And so what were these things? This was due to magnitude errors, right? This one was due to angle errors, right? So what we told you last week is that we said that this should equal F times delta theta, where delta theta is in radians. Right? And then this one is just basically your magnitude error that you would have got when you did your trials and you did your little averaging and finding your uncertainty of each magnitude. So what I did in the lab is I called this thing, I believe I called this perpendicular, this guy right here, and I called this guy delta S. Again, that, oh, I did it the other way around, sorry. This is delta S. That's that senrect. This is parallel, right? So, so there's those are those pieces. And then what we said is if we looked at the directions, why is this the case? So why was that the case? Well, they're perpendicular contributions. This one goes like this, and that goes like that. So you see, this is 0, right? It's clear because that's the way that we've resolved those errors. And so then we just put it pretty much back together, right? if we want to know how big this is, what is it? The magnitude. What would you do? What would you say? Pythagorean theorem, right? Do you agree?
We do delta S and delta P.
Perfect. So we would say F parallel squared plus F perp squared, but we said that that was this, right? So this guy we call delta S squared. This guy right here was delta P squared. Alright? So that's all it is. We're just putting the pieces together now. How big are these things? So this is for each one. So you evaluate for each one of those forces, right? You have 3 of them. So for each one, you're going to get, like, you know, that average is going to be, well, you'd have to look at how big was the uncertainty. If you looked at your, you know, when you measured your forces, the magnitude, there's what you're going to get for that, let's say T1 or something. You'd find maybe 0.2 Newton uncertainty there. Then what else? Well, you'd say, well, maybe it was a 10.3 Newton force. And then you'd say, well, 10.3 times angle in radians, maybe 1/60th, I don't know, something like that, right? We said, we estimated, you put that together, do it for your next one, add them up, take the square root, there it is, all right? So it's kind of a quantitative way of doing it, but we're trying to calculate now what that force you found should be, given your mistakes, you see? So we're comparing two things. We have a hypothesis. We made mistakes because we don't know the magnitude, we don't know the angle. Okay, fine. You kept track of your magnitude mistakes when you did your little analysis of your different trials. You know roughly what your angle mistake is. Okay, well, let's put the pieces together and let's see if indeed those things all add up in such a way that it causes you to get that little arrow that you found on your diagram. You see? So we're trying to understand what's caused it. But, I mean, let's face it, it's just an excuse, right, for trying to get you to think a little bit, right? Maybe do some little things with vectors. Maybe look at this idea of averaging over things. Maybe throw in a little bit of dot product there. So it's trying to use some of these things to actually get information. That's why I chose to do it. But I can tell you what is the history of this is that I think in the past, what I did is I had a question at the very end that said something like, well, try to estimate, you know, what your errors would do to get your net force. Is it consistent? Or, you know, how do you estimate your angle errors? And everyone would come and ask, I can't do this. I have no idea how to get this thing. And I just, well, okay, fine. And I would go through and I said, dang it, I'm just going to write up the way you do it, you know. I'm going to read the people through the whole thing. And so it's just, that's where it came from. Now, I wouldn't, you know, you are Physics 21 people. Physics 8, I wouldn't do that. It'll be a little bit too much, you know, stress level for them. But, you know, anyway, for you guys, you should try to just get familiar with it. It's just exposure to that type of reasoning, and, you know, it's going to come up in your calculus class and other math.